Now here for our last video in section 3.2, we're going to get a new definition here. And that definition says that a function f is differentiable. So differentiable. Okay, a function f is differentiable on an open interval from a to b if f prime of x exists for all x in the interval from a to b. Okay, and that is the definition. There we go. So we are defining what it means to be differentiable. This is the idea of differentiability. Okay, and basically this means that we are able to take the derivative. So the derivative exists is the same thing as saying the function is differentiable. All right. Now for the derivative to exist, keep in mind that our definition of the derivative is a limit. That limit as h approaches 0, f of x plus h minus f of x over h. So that limit must exist in order for the derivative to exist. So it's literally a does the limit exist or not type of problem. Okay, so couple details on this. This new word, differentiability, that just refers to the process of taking the derivative. The process of taking the derivative is also referred to as differentiation. Differentiation. Okay, and this is a little foreshadowing for you, that relates to something in section 3.9 called the differential, which is a big part of derivatives. So derivatives, differentiation, differentiable, differentiability, they all go together. All right. Now, another note here. If a function f is differentiable at a certain point, let's say x equals c, then we're guaranteed that it is continuous at x equals c as well. So that's kind of nice. We looked at continuity back in section 2.5. And this is a way to see if we've got continuity. If you can take the derivative of the function at a certain point or on a certain interval, then you have continuity at that point or on that interval. So yeah, that's a good thing to know. Now, another good thing to know about this statement is that it only goes one way. If it's differentiable, then the function is continuous. It does not go back the other way. So if a function is continuous, that does not imply that it's differentiable. So make a little teeny tiny note here. Converse of this is not true all the time, at least. Continuous does not imply differentiable. Okay. And we'll actually see an example of that in this next point here, when we look at some things that cause a function to not be differentiable. Okay. Now, a lot of these things that cause a function to not be differentiable match up with things that cause limits not to exist, because that's a key component of differentiability. a way of interpreting it. So some things that cause a function to not be differentiable are vertical tangent lines, okay, because remember that also the derivative represents the slope of the tangent line. So let's note here, derivative f prime of x equals the slope of a tangent line. And a vertical tangent line, or a vertical line in general, has no slope. The slope is undefined. So that means there's no derivative. So no slope, no derivative. Okay, so vertical tangent line, not good. Derivative doesn't exist at that point. Okay, now other things that cause f to not be differentiable would be discontinuities. Okay. So that would be, of course, your vertical asymptotes. Okay, that would kind of match up with the idea of vertical tangent lines there. Jump discontinuities would also not have a derivative because one part of your function might be coming in like this, and then here's another part of the function. How are we going to make a tangent line to that? We're not. So a discontinuity like that would not give us a derivative. So discontinuities in general, including also rapid oscillation, or wild oscillation, as the book is fond of calling it. Okay, so rapid oscillations, general types of discontinuities, jumps, holes, vertical asymptotes, oscillations, and then the other one that you might not expect from the limit type of definition is sharp corners on your graph, or something called a cusp. Okay, so a sharp corner on the graph is, well, literally what it sounds like. So that would look something like this. That right there would be a sharp corner at x equals c. And our derivative does not exist at that point because if you're looking at the two different sides, right-hand side, left-hand side of that point, it looks like you've got one tangent line going this way and you've got another tangent line going this way. And it can't really resolve itself there as to which tangent line to use. So our derivative doesn't exist there. We don't know which slope of which tangent line, and it doesn't match up there. So on these, the left and right hand limits don't match each other. So left and right hand limits don't match. Okay, so yeah, at a sharp corner like that, or a cusp is just an even more extreme sharp corner. A cusp looks something like this. You can have a little curve, but it comes to a very, very sharp point. Okay, so our functions there would not be differentiable at those points. So not differentiable. Okay, because again, we don't have a resolution of where that tangent line should be, what slope it should have. So Those are sharp corners and cusps. And these four things are really what you need to look for places where a function is not differentiable. A lot of functions are generally pretty well behaved in this class. So watch out for these certain things: vertical tangent lines, discontinuities, oscillation, which we don't even see that much when we get, wild oscillation. That doesn't happen too often. And then these sharp corners or cusps. So there you go.